Hey there, AP Calc students. Time for our final chapter of the whole course, Chapter 7, Applications of Integrals. And so this is the last few video lessons you'll get stuck hearing from me. Anyway, let's look at Lesson 7.1 today, the integral as net change. So in this lesson we're going to look at a few different types of problems. We're not going to look at all of them on this video because that would get too lengthy, but we'll be doing some of these things in class obviously. But one thing to keep in mind, I think on this chart will help you organize things a little bit. We have the types of problems here that we're going to look at and really what the integral represents in each case. We've seen the first case before where we have some velocity graphs, and of course the integral in its basic form really meant the area under a curve. And so if we're talking about a velocity graph, the area under that curve would really represent distance. We'll look at some practical examples here of some situations where we have a rate of consumption, some type of business or industry type situation, and here the integral will represent the total consumption, or maybe a total amount of money spent, or something of that nature. And then finally we'll look at this type of problem, force. Those of you in physics will recognize these types of problems, and the integral then will represent the actual work being done. So here we go, let's look at a couple of these instances. Alright, here's kind of the famous example. We looked at some of these particle problems earlier and we're going to revisit them again in this chapter. So what we have shown here on the right is the graph of the velocity of a particle moving along the x-axis. Again, this is kind of weird looking when we see a graph that looks like this, but the particle is just moving back and forth along the x-axis. We know that it's going to start at x equals 2 when t equals 0. So where is this particle at the end of the trip? So the key thing here we're looking for is the distance, or the area either under or over the curve. So for instance on this first case here, okay Puma, get out of the way. What we have here is, let's look at the area of this triangle that goes underneath the x-axis like that. And going to change the thickness here so it looks like this. What would be the area of that triangle? I think we can see, we know the area of a triangle is 1/2 base times height. Do you see that it looks like this base here has a length of 6, and the height, as we can see, has a height of 11. So 1/2 base times height would be 1/2 6 times 5. Don't, Puma. Get out of the way. Alright, now she's out of the way. So 1/2 of 30 is 15, but because this is underneath the x-axis, we have to say that that is negative 15 for the value of that particular integral. Now look at, here's what Puma did up here. I'm going to erase this. Alright. Now we want to look at the area of this region right here. Notice that's above the x-axis, so that's going to be positive. So let's take a look at that. That's a trapezoid. That's going to be 1/2 times the two bases, which I think you can see are going to be 4 and 3. And then I also want to multiply that by the height. The height in this case would also be 3. So 7 times 3 is 21. Half of 21 is 10.5. Now that will actually be positive in this case. So what I want to do then is combine these two things for my final answer here. And so negative 15 plus 10.5 is negative 4.5. So where is it at the end of the trip? Well, I have to take negative 4.5 and I have to add that, or combine that with the initial position, which is 2. And so my final answer for this is negative 2.5. That's where it is in this particular case. Alright, now the total distance traveled. Here we just really look at the positive part here when we're talking about just total distance. So we're going to treat this distance here as positive, and this is positive. So basically in this case it's just going to be 15 plus 10.5, and so that's going to be 25.5 for a total distance here in this case. Kind of strange, but we'll get the hang of it as we go. Alright, now here's another example here. We have this particular function, 6 times the sine of 3t. It's graphed between 0 and pi over 2. And this is one of those goofy particle things again. It's just moving back and forth, but it is based on this thing here. We want to know when it is going to the right, when it's going to the left, and when it's actually stopped. And you'll remember some of this from previous chapters when we looked at it. By the way, this is between 0 and pi over 2. This place right here, let me just mark this on the graph, this is going to be pi over 3. I know that because 3 times pi over 3 is just pi. I know the sine of pi is 0, so that might help us a little bit. Now, it's going to be going to the right when this velocity, and by the way, this is can be considered a velocity graph here, when this is going to be greater than 0, and so that is going to be placed, basically that's going to happen when my time here is between pi over 3 and 0. So that's when it's going to the right. When is it going to be going to the left? Well, of course, that's when my velocity is going to be less than 0, and that's going to be when t is between less than pi over 2 and greater than pi over 3. And when is my graph going to be stopped? Well, that's going to be right at this region right here. It's going to be stopped at pi over 3 when the t value equals that. All right, so that kind of makes sense. Maybe you remember some of that from previous chapter. Now, the displacement, and here's the key idea here, that displacement is basically going to be what the value of the integral is. Displacement is the value of the integral. We'll emphasize that quite a bit in class. So really what I want to do then, in this particular case, is I want to take that integral between 0 and pi over 2 of 6 sine 3t. Now this is a definite integral. We can use our calculators for this, which we'll check here in a second. Let's just see if we can remember how to do this. Remember, I'm looking for the antiderivative. I can pull that 6 out of there. The antiderivative of sine is negative cosine. So it's going to be negative cosine of 3t. But remember, if I took the derivative of that, I'd have to multiply by 3. So I have to counteract that by also multiplying by 1/3. And so when all is said and done there, I'm going to have negative 6 times 1/3. So that's going to be negative 2. And the cosine of 3t, I'm going to evaluate that between pi over 2 and 0. So I'm just going to write it like this. By the way, the cosine of 3 times pi over 2, 3 pi over 2, that's going to be, if I think about that, let's see, the cosine of 3 pi over 2, that's going to be 0. Remember, that's down there at 270 degrees. And then the cosine of 0 is 1. So really what this is going to end up to be is a value of 2. That's going to be my displacement. We'll verify that graphically here in a little bit. Now the total distance then, again similar to what we did before, is going to be the value of this integral plus the value of this. And we're going to think about this in terms of absolute value. And so I'm not sure I'm going to take the time to go through this on the video right now. I'm going to go to the other slide and kind of show you how we did. We could certainly do this algebraically. So here's verifying what we came up with on the graphing calculator here. Here's my displacement. I did that whole integral here. You can see the two shadings, but the value is 2. The total distance, if I do this on my calculator, I had to split this up into 2 parts. This is 4 from 0 to pi over 3. This is negative 2 from pi over 3 to pi over 2, but when we talk about total distance, we're talking about absolute value, and so the total distance then would be 4 plus 2 which would be 6. That's the total distance that that particle had traveled. Alright, last slide here. Here we'll talk about force a little bit. And we refer to this famous formula here called Hooke's law, which says that force is equal to some constant times x. And the idea that we showed in that first slide, again, is that if I take the integral of force, that's going to give me work. That's what I'll be looking for here. So notice the problem says that it takes a force of 10 newtons to stretch a spring 2 meters beyond its natural length. How much work is done in stretching the spring 4 meters from its natural length? Well, based on this formula here, we can say that the force is 10, and we're going to actually look for that k value here. So 10 equals k times 2. Obviously then, if I divide both sides by 2, k is going to equal 5. That's that constant. Now I go through this again. Well, I know what my constant is now. Now here's where I take my integral, and this time I take my integral from 0 to 4. Again, the natural length is considered to be 0. That's where it should be. And then we have 4 meters is where it's going to be stretched to. And I take the integral of 5x, like that. These are pretty easy integrals after some of the ones we looked at last chapter. Remember, I can pull my 5 out of there. The integral of x, by the way, I forgot my dx in here, didn't I? The integral of x, of course, is x squared over 2, and I want to evaluate this between 0 and 4. And sure enough, if we do that, this is going to be 5. And then if I put 4 in here, 4 squared is 16. 16 divided by 2 is 8. If I put 0 in there, of course, I get 0. So I end up with a force of 40. The units are kind of strange, kind of newtons per meter, or newton meters, I think, is how that works. All right, so that is just a little brief intro on some of the stuff that integrals can be used for. And we'll see you guys in class and talk much more about this. Thanks.